All right. We're in section 9.7, and we're talking about Taylor polynomials. So what we want to do in this section is we want to develop a procedure for approximating functions with polynomials. Why would we want to approximate with polynomials? What's the benefit of approximating with polynomials? Integrals and derivatives. So polynomials are a little easier to work with. They're a little friendlier, right, than some of our complicated functions. So that's one reason. So when we're doing calculus with polynomials, it's easier. It's also, in general, just easier to compute with polynomials, plugging numbers in and evaluating them than some of our difficult functions. In more kind of a more modern take on it, this wasn't the case when Taylor polynomials were developed, but computers are really good at addition mostly, and polynomials allow us to approximate these complicated functions using basically addition. Multiplication is repeated addition, exponentials are repeated multiplication, so we can model them with easily with computers. So that's one benefit, is that using polynomials lets us use computers to do various things. So what we're going to do for this section, we're going to call our polynomial p of x. So that's our polynomial. And we're going to start our procedure. We're going to start our procedure by we're going to pick a point C in the domain of our function. And this is in of f. F is the function we want to approximate with this polynomial. And just some terminology, we're going to say our polynomial is expanded about C. The other way here is centered at C. So the procedure we're going to follow here, what we're going to do is our first requirement. We're going to make several requirements on this polynomial. Our first requirement is that we're going to require that our polynomial at C equals our function at C. And we can think of Taylor polynomials, we can think of these approximations as we have a point on a particular function. And we see it at one particular time. And then we come back later and we want to know where is that point on our graph of our function. Well, our first guess, our easiest guess is, well, let's start with where it was before. So that's why we're saying the polynomial equals the function. We're starting with where it was before. We want to make our prediction a little more accurate, what this function is doing. So we're going to say that the first derivative at C has to equal the first derivative of our function at C. So now we're saying we know something about how quickly this particle was moving along this curve. So we come back, we know where it was before, and we know how fast it was moving. So that gives us a better idea of where it might be. And we continue this process requiring the derivatives of the higher derivatives of our polynomial to agree with our function. So we continue. So we're going to say that p double prime at our point has to equal f double prime at our point, comma. The third derivative has to be the same. for as many terms, as many pieces as we want, as close as we want our approximation to be. So we're going to require that the function agrees and that its derivatives agree, depending on how many terms in our polynomial that we want. And this is going to give us our method for developing this polynomial, the requirement that these all agree. Oops, and this should be P triple prime at C. Yeah, F triple prime at C better equal F triple prime at C, or we're in trouble. So let's just write out our polynomial, the general expression for this polynomial, and come up with how we're going to write our approximation. So we're going to say that P sub n. So we just have n terms in our polynomial. We have this constant term at the beginning. And this is what we want our expansion about C to look like. Plus, and we go out for as many terms as we want. And we want to determine these constants A0, A1, A2, etc. And we can determine the constants by our requirements that we've placed on the function and its derivative. So let's take the derivatives of this function. So we're going to say that P prime of n, we're just going to take the derivative. Well, that constant term goes away. And we just end up with A1 plus 2a2 x minus c plus 3a3 x minus c squared plus dot 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 plus n x minus c to the n minus 1. And we're going to continue taking derivatives. P double prime. We're trying to see a pattern here so we can determine these constants. So we end up here with 2a sub 2 plus, and I'm going to write this as going to write the 2 in front here, and then we keep going. And let's write out one more. Oops, sorry, this should be, there we go, plus, and then down out here we have n times n minus 1 times n minus 2. Oh, and I forgot my a sub n here. N minus 2, a sub n, x minus c, n minus 3. And finally, this is, if I take the nth derivative, continue, all I'm left with after n derivatives is n times n minus 1, n minus 2, dot dot dot, times 2, times 1, times a sub n, after we take n derivatives. And now we're going to equate our function and the derivatives, our polynomial approximation and its derivatives when x equals c. So I'm going to plug in x equals c and equate the function and equate its derivatives. So that was our requirement, is that these things agree when x equals c. We pick the point and we say these things have to agree at this particular point. So when x equals c, I get that p sub n of c equals a0. So when I plug in c here, all of these terms go away, and I just get this first term. I get that p sub n prime at c equals a1. P sub n double prime evaluated at c equals 2a2. And I continue, and at the nth derivative piece, the nth derivative of p sub n is n factorial times a sub n. And I equate these with my function evaluated at c. So f of c has to equal a0. F prime at c has to equal a1. F double prime at c divided by 2 factorial has to equal a2. And the nth derivative of n at c over n factorial has to equal a sub n. So I get these constants by equating these two terms, or these two expressions, and solving for my constant. So this gives me a way to find my constant. A0 is just my function evaluated at c. A1 is f double prime evaluated at c. A2 is f prime evaluated at c. A2 is f double prime evaluated at c divided by 2 factorial. And the nth derivative of n at c divided by n factorial has to equal a sub n. So that gives us a way to determine these constants.
Is b double prime n at c equal 2a2 or 2 factorial is 2?
2 factorial is 2. 2 factorial is 2 times 1. So I can write this as 2 factorial. So this gives us a way of determining these constants. Our constants are the function given by our function value, our function evaluated at c, and we divide by these factorials. This is 1 factorial, 2 factorial, go 3 factorial, 4 factorial, etc. So if our function has n derivatives, however many derivatives our function has, we can write a general expression for the Taylor polynomial expanded about c for our function. Is everybody good with how we came up with the expression for these constants for my Taylor polynomial? All right. So if f if our function has n derivatives and we're interested at our particular point c, then we can say, in general, our Taylor polynomial expanded about x equals c is f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial x minus c squared plus dot 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 all the way to the nth derivative over n factorial times x minus c to the n. So this is how we're going to write our Taylor series expansion that guarantees that our function agrees with our approximation at C. Our first derivative agrees with the first derivative at C. The second derivative agrees. Third derivative agrees, etc., etc. For as many derivatives as f has, or for as many terms as we want to include in our approximation. And we call this the nth Taylor polynomial. For f at C, expanded about C, centered at C, something like that. And depending on the function, if we're looking for an approximation near C equals 0, so we're looking at an approximation near C equals 0, then we get the Maclaurin polynomial. And we can write, that simplifies our notation a little bit. Then P sub n, our expansion, is just f of 0 plus f prime of 0 times x plus f double prime at 0 over 2 factorial times x squared plus dot 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 plus the nth derivative at 0 over n factorial times x to the n. And this is the nth Maclaurin polynomial. And here we're expanding about C equals 0. So Maclaurin polynomials are a little neater because we don't have this, a little tidier because we don't have this x minus c. We just have an x in there. And we will talk next time about if we have an infinite number of terms, how do we determine when this type of series, if we have an infinite number of terms, when that type of series would converge or diverge. And that's really the power of using these kinds of things, is we can determine where they converge and diverge, when we can use them as an approximation to our function, and when they're going to converge to the value of the function. All right, questions on our procedure? So really the process for Taylor polynomials is finding these function values and these derivatives at our point to write our approximation. That's really the work of Taylor polynomials, is finding these constants. This f of c, f prime of c, f double prime of c divided by 2 factorial, etc., etc. All right. So let's do a couple of examples of how we would use these, how we would apply these, and when we would apply we might apply a Maclaurin series or a Taylor series. So we want, for this particular example, we want the first 4. So I'm looking for P0, P1, P2, P3, and this is a comma. For our function f of x equals 1 over x, and we want to center at c equals 2. So we want to expand about 2. So the way I like to set these up when I have to find Taylor polynomials is I'm just going to list in columns f of x equals 1 over x, and then next to the column I have put my my function evaluated at my point. So f of 2 is 1/2. F prime of x. What's f prime of x is going to be what here? What is it? Negative 1 over x squared. What would be the natural log of x? That's the integral of integral. So we were thinking going the wrong direction. And then f double prime of 2 is minus, sorry, did I go to double prime? I was hoping that we were almost done. F prime, that's the bad thing about Taylor polynomials is there's a little bit of tedious work to do. Finding derivatives, plugging in numbers. So there's my f prime is negative 1/4. F double prime of x is, what is it? 1 over x cubed? 2 over, I have this 2 that comes down, so 2 over x cubed. And there we go, f double prime at 2 comes out to be what?
1/4.
1/4 again, but I have a positive this time. All right, f triple prime of x is
6 over x to the 4th, negative.
there we go, negative 6 over x to the 4th, and f triple prime of 2 equals
3 over 8, negative.
negative 3 over 8. Okay, and these are all I need, so I just need my function, first derivative, second derivative, third derivative for my first 4 polynomials. So p sub 0, my 0th Taylor polynomial of x is just f of 2. That's my first polynomial. It's just a constant. So this says that 1 over x at x equals, for numbers close to 2, is about 1/2. So if you're really close to 2, that would be a pretty good approximation. But if we're not really close, we need something a little better. So p sub 1 of x is my first polynomial, 1/2, minus 1/4 times x minus 2. P sub 2 of x is going to be these two terms, 1/2 minus 1/4 x minus 2, and then I have plus 1/4 times 1 over 2 factorial times x minus 2 squared. And we could multiply that out. I'm just going to leave it written that way for now. And finally, my p sub 3, my fourth polynomial is these three terms, 1/2 minus 1/4 x minus 2. And if I multiply these two out, I get 1/8 x minus 2 squared. And then my last term is minus 3/8 times 1 over 3 factorial times x minus 3, x minus 2, I was thinking of the exponent, to the third. So there are my first 4 Taylor polynomials. For x near 2, this would be a pretty good approximation of 1 over x at that number. Now what if we wanted to approximate 1 over 2.8? 2.8 is kind of close to 2. Could we come up with a better series to approximate something like 1 over 2.8. What function might we expand to find f of 2.8? 1 over 2.8. Anybody have an idea? Could center it at 3. And I'm thinking if we could do a Maclaurin polynomial, because they turn out a little nicer because we don't have these x minuses. So what I'm thinking is that 2.8 is a little closer to 3 than 2. So I want to expand. Just another option that we could do for this, for our approximation, is we could expand f of x equals 1 over x plus 3 about 0. So then we're expanding about 0, then because 2.8 is closer to 3, this would give us an approximation, a little closer approximation, we would hope, to 1 over 2.8. So just another way we could go about this. So let's look at this one. So we'll do a few Taylor polynomials for this one. So f of x equals 1 over x plus 3, and f of 0 equals 1/3. So 1/3 is a little closer to 1 over 2.8 than 1/2. So our first Maclaurin polynomial is a little closer to approximation to 1 over 2.8. We can take our first derivative. So f prime of 0 is minus 1/9. Take the second derivative, and we get two over x plus 3 to the third. F double prime of 0 is 2 over 27. And take our third derivative. We get minus 6 over x plus 3 to the fourth, and our third derivative evaluated at 0 is minus 2 over 27. So then my polynomials piece of 0 is just 1/3. My first Taylor Maclaurin polynomial would be 1/3 minus 1/9 x. My next polynomial would be 1/3 minus 1/9 x plus 2 over 27 times 1 over 2 factorial x squared. And my last polynomial would be all of these terms. Minus 2/27 times 1 over 3 factorial x to the third. So expanded, this is 1 over x plus 3, expanded about x equals 0. So I have, rather than the x minus terms, I just have the x terms. And to approximate 1 over 2.8, for this function, what would I let x equal? If I want to approximate 1 over 2.8 with this, what would x equal?
0.
A little closer. So I want to plug x in here to approximate 1 over 2.8 with this function. So what would x be? Negative 0.2. So I would plug in x equals negative 0.2 into this polynomial to approximate 1 over 2.8 with this approximation. And when I plug that in this series, for this approximation, we get P3 of negative 0.2 gives me about 0.3571. For our original, where we expanded about x equals 2, we get that P of 3 is P3 of 2.8 is approximately 0.3480. And what does your calculator tell you? Josh, when you plug in 1 over 2.8, what does it give you? What does it come out to? Just one over 2.8. Just 1 over 2.8. I just want to know what you were calculating up. 0.357. So this approximation is a little closer to we're hoping that the algorithm that our calculator uses is a good approximation. So this approximation is a little closer to the actual value of 1 over 2.8 than our first approximation, which was 1 over x evaluated at 2, or centered at 2. So that tells us that maybe 2.8, that 0.8 is maybe a little too far away to approximate with just three terms of our Taylor polynomial. So the second one, this one expanded about 0, gives us a little better approximation because 2.8 is a little closer to 3. So just a couple of examples of calculating our coefficients for our Taylor polynomials and Maclaurin polynomials. So tonight's homework is just a little practice with this. What we will do tomorrow is expand on this and talk about an infinite series of this type of polynomial and start working with those. All right, there you go.